Mr. Ali.
Mr. Ali.
Hello, can you hear us, Mr. Ali?
Now, I'm sorry for that. That's because somebody used another microphone for this PC, and the settings for the audio settings was changed. It's okay now. Okay. We are talking about the mass and the weight. I will share my monitor with you. I will talk about it again. We was talking about the mass and the weight. The mass is the amount of matter in the object, and the weight is a force due to gravity. Okay, and the weight in the outer space is approximately zero because the gravitational field goes to zero away from the planet. Okay, at the surface, G has a maximum value which is 9.8 meter per square second, and the formula for the weight is mg. M is the mass. It's just like it is from Newton's second law. M is equal F is equal to ma. We have the weight, which is a force. Mass is the mass. A is g, which is the acceleration. Now, we will talk about the mass. It is just a mass. We can measure it using the equal arm balance. We have unknown to measure the mass. If we have unknown mass, M is unknown, and we have another mass which is known. For example, 1 kilogram. We can use equal arm balance. Just put one of them at the, on the side and the other on the other side. Then, if one of them is heavier, more heavy, then it will not be in balanced way. We need to put the known mass in the opposite side. If they have equilibrium, then the two masses are the same. It is simple. So we need to use the equal arm balance. Now we have electronic probes to measure our mass and different masses. Okay. Also, we have these electronic probes to use to measure the weight. We can also measure the weight. In my place, I have a balance or scale to measure my mass. It's about 90 kilograms. When I see it in pounds, it's about 200, I think, something like that. But this is not the weight. This is my mass. So when you ask me what is your weight, if I told you it is 90 kilograms, so I am wrong. If you ask me what is your mass, this is my mass. My weight, I need to compute it or to measure it in Newton. Okay. Now, simply, if my mass equal to 90 kilograms, then my weight is equal to 90 multiplied by G, which is 9.8, approximately 10. So my weight is equal approximately to 900 newtons, right? Now we will talk about G small and G capital in general. We have Newton's law, which is the general law of universal gravity. Gravitation. Gravitation. Okay. This is one of the most important laws in physics. F due to gravity is equal to a constant, universal constant, which is G multiplied by mass and another mass, M1 and M2 over R squared. What does that mean? Okay. If you remember or know the story of the falling apple to the ground when Newton was sitting under the apple tree, he asked himself, why is there is attractive force between them? Then he know we have a mass, we have another mass, we have a distance between them. This distance is R. What is the ratio of the force between these objects? I'll talk about that. To know this important application, we have two bodies, M1 and M2. Now, in this course, we are talking about point objects. This is not point object. The Earth is not point object. Why? Because if you need to take R, the distance between these two objects, one of us will take this R. Another one will take this one. He's right. But one of us will take this R. He will assume the center of mass and the other center of mass, and he will take that radius between them, these two center of masses, and he will assume that all the mass at the center, and that is the right thing. R is the distance between the two center masses. Now, we have a gravitational force between them. This force depends on the mass and the mass. What if we have smaller masses? M1 and M2. And the same R. What do you expect about the force? It will be smaller or bigger?
Smaller.
Smaller. Any two objects in the universe have attractive force. This razor and the monitor. But the force is very small because their mass is small. So if the mass gets bigger, then the force gets bigger. In this case, we can write F proportional to M1 and M2. If M1 gets bigger, then the force gets bigger. And also the same for the mass number 2. What about the distance? If the two masses are closer together, then the force gets bigger. Okay. If R gets larger, then the force gets smaller. Now we are attracted to the Earth, but we are not attracted to Jupiter or to the Sun. The Earth's force, dominant that Sun force on us because the Sun is far away from us. Okay. Now, this means we have, if R gets bigger, then the force gets smaller. This proportional is R, 1 over R. But we have two masses. We have R from mass number 1 to mass number 2, and we have R from mass number 2 to mass number 1. Okay, so we have R squared. This is the inverse. Okay. In physics, to solve any equation, we can't solve the proportionality. We need to have it as equal sign, right? We need anything with equal sign to solve it. So we don't have anything else to solve the problem. For example, the color of the object doesn't matter. The name of the object doesn't matter. Okay? Just this is the most important parameters, the masses and the radius. or that distance between them. The constant of proportionality, to remove the proportionality sign and to put equal, this is by experiment they found it equal to G. G is a universal constant which is equal to 6.67 multiplied by 10 to minus 11 with its unit, which is Newton meter square over kilogram square. You can't find that. This is G. It is a small value, 10 to minus 11. That means we need masses more than this magnitude to have the force sensible, and radius small enough to sense that force. Now to solve an example of that. Any questions so far? We are on Earth's surface. This is me again. The Earth radius from the center, it is big R, RE. My center of mass approximately at this point, me and everyone, okay? Its altitude from the Earth's surface approximately 1 meter, approximately, right? The Earth radius is equal to, the average value is 6.4 millions multiplied by 10 to 6, which is million, meter. Okay? My distance from here, which is R small, for me, Rm, is equal to 1. My mass, M1, is equal to 90 kilograms. Right? The Earth mass is equal to approximately 6 multiplied by 10 to 24 kilograms. It is a huge, but not huger than the sun. We'll see that the sun has a bigger magnitude. So, what is the force between me and the Earth? F between me and Earth is equal to G, which is 6.67 multiplied by 10 to minus 11, multiplied my mass with my mass, which is 90, M1, 90, the mass of the Earth, which is 6 multiplied by 10 to 24, over the radius. The radius, as we learned from before, it is the radius between my center of mass and the Earth's center of mass. The Earth's center of mass is R Air is equal to 6.4 with multiplied by 10 to 6. So we have 6 zeros. Okay? We need to put them with this, we need to move the decimal point 6 steps, then it will be 6 million meters. And my radius R for me is equal just to 1 meter. When we need to add 1 to 6,400,000, it will be with 1. We need to put 1 here. Is it logical to keep this number and go away and use it everywhere we need to use it? Because we just have 1. For example, if you have $1 million and 1 cent, you will not tell others I have $1 million and 1 cent. Always. That's enough. I have just $1 million. Okay? So we will cancel my radius. okay, then we will use the dominant radius, which is R A. So our R small is equal to R A plus R for me. I will cancel this. So R will be, a smaller R will be the radius of that planet. Because I am at the surface of that planet. But if I am outside away in the space, then I have a sensible radius away from it. We will see that. So that it will be 6.4 multiplied by 10 to 6. Any question now? Okay. This will be equal to the force between me and the earth is equal to F is equal to, I've computed by the general law of Newton, is 800 79.7 Newton. Okay, what if I need to compute it in this way? F is equal to weight, which is equal to M multiplied by G. This will be equal to 90 kilograms multiplied by G, which is, by the way, 9.8 is approximated value for G. The value of G depends on the altitude of the Earth's surface. G is maximum at this is at G is equal to 9.8 approximately with different, with more digits at sea level. Okay, at mountain G will be less than this value. Outer space less than this. Okay, so this will be equal to 882 newtons. The difference is less than 3 newtons. 3 newtons mean I think this one will be 3 newtons. Okay? Because 1 kilogram is approximately 10 newtons. The bottle of water, which is a 3 kilograms, it is 3 newtons. Okay? Not that difference. Just 3-4 fingers from my hand. So they are the same. Okay? They are in general the same because G is approximated. R of the earth is approximated. Mass of the earth is approximated. Then they have the same physical meaning. And by that, I can compute G because both forces are the same. So the left hand side is equal to right hand side. So I can find G from this value. I'm talking about air. Okay. So the force is equal to G capital M1, which is my mass, M for the planet, which is capital, over R squared, which is equal to mg, which is equal to the weight, which is the force. Okay. Now we have m for me, the both sides. I can cancel it, or I can divide over m1 over m1. Then I can cancel it. So I have G capital multiplied by the mass of the planet over R squared is equal to G. At the surface, R is equal to R of that planet, of air or moon or sun or whatever. So I can compute G for any planet. We have example now. computing G for the sun, for the moon, for the earth. You can compute it for Jupiter and for any different planet. Any question? Anyone know, I'm asking now, how much your mass on Earth, how much your mass? Give me a number also. 190 pounds. It's, you don't need to convert it, but it is approximately, let us say your mass is approximately 80 kilograms. Right? What's your name? What? Ronaldo. I'm sorry if I write it wrong way. Okay. Ronaldo. Is that right? No.
You can say Bird.
Eh?
Bird. B-E-R.
So just take assume it Ronaldo. I'm sorry for that. I'm not good in that. Okay. This is on Earth. What was that? Myself in that example. Your name is this. Your mass is this. Your weight is equal to mass 80 multiplied by approximately 10, which is approximately 800 newtons. Are you agree with that? Okay. Now we are in different system. We are on moon. Okay. What is your name? It's the same. What is your mass? Does your atom and particles change from here to here? It is the same. So your mass is the same. It's equal to 80 kilograms. It is essential, or fundamental property of the object. What is your weight? Anyone know how much the weight will be, or how? Any one of you heard that the gravity on moon is 1/6 of the gravity on Earth? I don't know if anybody of you heard that, but we will compute that. Also, your weight also on a different heavier planet will be more. Okay, let us compute it now. We have 3 planets, 3 big masses. We have the sun, we have Earth, we have also the moon. One of the most important concepts in physics that the relations what we found in Earth are suitable to work elsewhere. Anywhere in the universe. So this relation is okay to use it in sun, at the surface of the sun, and also at moon surface. We can use the same equation. Now, the mass of the sun is equal to 2 multiplied by 10 to 30 kilograms. The mass of the Earth, as we said, MP is equal, MS equal to, as we said, 6 multiplied by 10 to 24. The mass of the moon is equal to 7.3 multiplied by 10 to 22 kilograms. The radius of the sun is equal to 7 multiplied by 10 to 30, by 10 to 8 meter. Radius of Earth is equal to 6.6 multiplied by 10 to 6 meters. The radius of the moon is equal to 1.7 multiplied by 10 to 6. This is 1/4 meters. We have important things. We have G is constant, universal. It is the same in all others. Okay. Now, if we need to use these givens for my mass, not yours, which is M equal to 90 kilograms, I will find my mass on each planet. Okay. So the force is equal, I will find G now. G, then I will find the weight. G is equal to G capital multiplied by the mass of that planet over R squared. R is the radius because I'm at the surface. Okay? This is for the sun. Okay? G will be equal to 272.4 meter per square second. For Earth, G will be equal to, after using the same formula, 9.77 meter per square second. If you approximate it, it will be 9.8. On Moon, this is G in Earth. This is G for Sun. Will be equal to 1.7 meter per square second. If you need to compute your weight on Sun, the weight is equal to your M multiplied by G at the Sun, which is equal to 24,516 point something. Which, newtons. Okay, your weight in air. This is your weight at the sun surface. At Earth, it is 979.3 newton, what we found from before. And your weight on Moon equal to 151.7 newtons, which is equal to approximately 1/6 your weight on Earth. Now, be careful. At the surface of Sun, your mass is the same, but your weight is very much huger than yours at Earth. If we have a box or not a box, okay. This is yoke. Which is GLC. Okay, its weight, for example, 2 tons, 450 kilogram tons, or 2,450 kilograms. How much its weight on the Earth's surface? It is 24,500 newtons approximately, right? On the sun, at the sun surface, your weight there, it is the same as the weight of the car here, because there is too much gravity on you. That's why the sun's hand can go away farthest down the Earth, race and Jupiter and Uranus and all of the planets, and can collect the planet's group around it. At the earth, we are familiar with it. This is our weight. We know that. This, our weight at the moon surface, which is 1/6 from our of our weight on Earth. So if you are jumping on Earth, if you are jump for 1 meter, okay, this force, what you put to jump this distance, will make you jump 6 meters, not just 1 meter, because the gravity on moon is much less than the gravity on Earth. Because of that, you see that astronauts wearing heavy clothes and a heavy bag, their bags, because they need to make them heavier. Because if one of them is they just wearing normal clothes, and one of them is forget his force and just make a strong push on his legs, then he will go away. Okay. You see, there's a John Connor film with the Princess of Mars. It's the same case happened with the person who traveled from Earth to Mars. He jumped very vast distances because the gravity of that planet is different than ours. Okay. Another thing now we'll talk about Newton's third law, and also we have any questions here? So if you need to compute the weight, you need to know the radius. At the Earth's surface, it is mg. It is okay. But away from the planet, we need to use the general Newton's law. And we see that there is a difference between the weight and the mass. The mass is constant for a certain body, but the weight is not. Depend on the mass of the planet and the distance between the two objects. Now, third Newton's third law. It is simple. Simply as you see, if we have there's nothing to write now. Now, we have Newton's first law, second law. This is the third one. We talk about the fourth one. No, it is not the fourth. It is more general than these three laws of Newton. This is the third law for Newton. If we have a force, active force between two bodies, then there is an active and interacting, or action and reaction between them. For example, if you have a bat hitting a ball, then there is a force acting from the bat on the ball. Bat, a big B, or yes, higher case of B, B, lowercase b for the ball. Then also we have a reaction from the ball on the bat. If you hit something, you can sense there is pushing on that bat. Also, if I push a wall forward, this wall is also pushing me backward. In this case, we have force and normal force, like this way. We have force and a normal force, which is a reaction. We have FMW, which is the same as FWM, which is equal to it, but in opposite sign, opposite direction. So if we have two objects, A and B, and we have a force between them, which is an interaction force, then it is the same as the force between B and A, but with opposite direction. As we see here also, a walking person, there is no walking if we don't have a reaction force, because our legs acting on the air, we are pushing the air or the ground backward, and the ground pushing us forward this way. It is pushing us forward, we are pushing it backward. If there is no friction force between me and the ground, then I will keep walking in my place. I will not move. Sometimes when you using a pen, you cannot write on some pieces of paper, sheets of paper, because there is no friction between the head of that pen and that paper. So you cannot write. Some types of chalks, when you come to write, it just slipping and do not write anything because there are no friction force. The friction force is important. And action and reaction law is also important in this case. If we have a mass over a table, we have the weight downward and the normal force upward. Also, the mass of the table acting on the ground, and there is a normal force between them also. In this case also, we have the sun and the planet. We have the force between acting from the sun on the planet toward the direction of the center of the sun. And also there is a force between the planet and the sun. The planet also attracts the sun. If I have your hand and pulling each other, you pulling me, and I'm pulling you the same force. But if you are stronger than me, and that's right, and you will pull me more force, then our force will not be zero. We don't have balance. Okay, if we have 50 newtons and 50 newtons, we have newtons as I mentioned. We have a balance, but if your force is bigger than me, larger than me, then you will pull me in your direction. Okay. This is also an important thing. Earth pulling me and track me by a force. What is that force? What we called it before? What is the force that the earth act on me and pulling me to its center? What is that force mean? What? The gravity, yes. What is that for me? It's my weight, right? The force attracting the earth attracting me by F from earth on me, because of the existence of them in nature. In Newton's third law tells us there is also a force between me and earth, or me acting on earth also by the same force. So if the earth acting on me by my weight, which is the earth attract me by 879 newtons, also on me, this is toward the center of earth, also me attract the earth by the same force. The earth will, another example also, I will not jump. If I leave this to go down because of the force, because it's weight. Also, there is a force between this body and the earth, and this body attract earth to its direction, but this motion is negligible, it's almost zero. Okay, because we can't compute it. It is computed. So simply, this is the Newton's third law. any action has a reaction, the same magnitude, different in the opposite direction, and these reaction forces are in two different objects. Is that understood? Some people, when they need to fix their car, for example, we have a truck, and this truck is not working, you need to push it. This is all of you pushing it from different places, but this is me pushing it from here. I need to help you. Who's the smartest one? Of course, it's me, right? Because my force, this is my force, and this is my action force, and this is my reaction. So the action and the reaction both in the same object. So in this case, the object will not move. So I am very smart here, right? Thank you. Now, we will move to the final part of this lecture, and I will tell you something about the homework. We have free body diagram. You will face this a lot in the lab section. Free body diagram, it is just drawing the problem, the example, to understand it and make it easy. To see at the end if we have, just like what I did here. This is these forces that arose are a free body diagram for this system. It will show me if we have a total force or not. Do we have any total force in this case? Yes, we have. We have 10 to the, you're right. If we have it 50 with 50, then the total force is 0. The free body diagram is to draw the forces as vectors with magnitudes, and the direction is important also. This is not the total free body diagram because we have a force between our arms. So we have a tension force for this arm, and we have another tension force for this. So we have T1 and T2. And all the forces are the same. The tension is equal to the tension equal to these forces. For the pendulum, we have the weight downward, and we have the tension toward the thread or the string. Between the string and the ceiling or the suspension point, we have a force also, tension force and the normal force. This is a balloon. We have a weight downward and the floating force upward. Which one is huge, is bigger? Then the body will accelerate to that direction. Also the same for this ramp. If we have a friction force, and the body will move downward. We have the weight downward and the normal force, normal to that surface motion, and we have the friction force. Considering the body, the object, just one point, and drawing the force from that point is the free body diagram. It helps us to understand that problem. Any questions so far? Okay. Also, we have time. Yes, we have time. Also, some examples as a tips to help to solve to finish the third homework. By the way, the tutoring hours are ready now. You can visit the tutoring hour as I send it by email and by announcement. You can use it to solve the homeworks to help for that, and also you can take a help for doing the lab section. If we have three objects, M1, M2, and M3. We have a strength between them. We have a force. This force, for example, is 30 newtons. For example, they have the same mass. Let us say 5 kilograms, 5 kilograms, 5 kilograms. I can change that. Okay. What is the acceleration of all the group? What is the acceleration for? This is M3. So 3, 2, 1. We need to also to know the free body diagram. We have a tension here. This string. Also, we have a tension. This tension is 2, 3. Between 2 and 3. This tension is between 1 and 2. They are not the same. What is the acceleration of the first mass? What is the acceleration of the second mass? What is the acceleration of the third mass? They are all the same because they are connected together. What is my acceleration inside the car? It is the same as the acceleration of that car. So the acceleration, in general, I can know it by knowing the total force. What is the force? It is 30 Newton. So F is equal to M multiplied by the acceleration. Mass. The mass is the total mass. The force is acting on all the masses. It is M1 plus M2 plus M3 multiplied by the force, which is 30. This is equal to 5, which is 15 multiplied by 30, which is how much? 450. Meter per square second. Okay, what else? Also, we have a tension force in this one. This one. T3. The main one. Okay. What is the tension force? The first one, the second, and the third one. The third one, I need to ask you something. If this string break, it is not. Is it curving? No, it is stretching. The mean that stretch, the mean of stretch means the force is not less than the tension force. The tension force is not less or and not bigger. Okay, if it is bigger, then it will be cut to be to two pieces. So the tension force is equal to the applied force. T3 is equal to the applied force F applied, which is equal to 30 newtons. Is that simple? What about the tension force T23? If our system, our universe, me and you, now we are sitting on this chair. This is a chair for all of us. We will see that we are under the action of this force, right? Now we are not in that system. We are in this system. What is the external force on us? We don't know about this one. We know about just this one, right? We don't see the outer force. It is far away from us. We see just T23. Okay, so T23, this one, is the important force for these two bodies. So this system goes under this force. Just it does not know anything. It doesn't know anything about this one. So what is the mass for my system? Is M1 plus M2, right? Because I am here. the acceleration?
450.
I am in the same. I am in the same acceleration as all of that system because we are all moving together. Look at the Earth. We are here, and this is the sun. The sun attracts us and attracts the Earth. All together we are going around it. But do we care? Are we caring about the force of the sun on Earth? No. The Earth, just the Earth, with all of its components, care with that. But we just care about our force on Earth. So this is we. This is the force of Earth. This is the force of sun. This is the Earth with us. Okay? Now, what is the acceleration? It is the total acceleration for the system. The total acceleration for the system is 450. It is the same. But we have the same acceleration for two masses, which are 15 plus 15, which is 30. Multiplied by, is that right? No. This is wrong. This is wrong, right? Yeah. The acceleration is equal to the force divided over my mass. That's a huge number. Right. This is wrong, I'm sorry. The force is 30 divided over 15, which is equal to 2. This is logic only. Meter per second. So the acceleration is 2. So the tension force is 60 newtons now. Again, I'll draw it in a simple way. So we have 30 here in newtons, which is equal to T here. We have 30 over 15 will be 2. This is 10, not 30. This is 5 and 5. I take 15 and multiply by 2. This is 10. Will be 20. I have 30 here. This tension between 2 and 3 is equal to 20. I'm looking now for 1, 2. By the same way, I have this mass with the same acceleration. How much the mass is? 5. I will not do the mistake again. And the acceleration is equal to 2. How much the force acting on that force, that mass? The force is the tension. 1, 2 is equal to the mass multiplied by the acceleration, which is 10 newtons. So this is 10. Because the three masses are the same magnitude, have the same magnitude, have the same mass, that the 30 newtons is divided equally between them. 30 newtons become 20, lose 10 newtons here, lose 10 newtons the second one, and the third 10 newtons at the third one, for the third one. So the mass is the same for all of them. The acceleration is the same for all of them, but the acceleration, yes, the mass is changed, and the force, which is the tension, is the same. We have a kite. This is a different example than the homework example. if we have a kite, this is the string. So we have a tension force, that string or thread, right? We have the weight. You tell me, what we have, what is the forces that we have? We have the tension in the thread, we have the weight downward, we have some what is this? F applied due to the wind. Okay. If the mass is equal to what? Where's the normal force? Upward. Okay, she's asking about normal force. It's a good way to think in physics. Then we have a flying kite. Just one object. Doesn't interact with any object, just the thread. Okay. We have a normal force between the thread and the kite at this point. Okay. The total force at this point is 0. We will see that. We will not put it in the external forces. We have normal force inside the point of interaction, contact point, and we have a normal force from the thread this direction. Okay? We will see this force now. You can see. But all the total forces are equal to how much? To 0, because the kite is standing at stationary. Okay? We have the mass of that kite, for example, half kilogram or 0.4. Then how much the weight? This is the mass multiplied by g, which is equal to 0.4 multiplied by 10 approximately. I will use it 10. Okay, which is equal to 4 newtons. So the weight is 4 downward. If the angle in our example will be 60 degrees down the positive x-axis. Okay, and the tension force is equal to 50 newtons. I'm asking now how much that applied force. If total forces are equal to 0 as a vector, which means total Fy equal to 0 and total Fx equal to 0. How can I start solving this example? Simply by taking each direction alone. The normal force will not, we don't have any surface here to have a normal force upward. Okay? We don't have a surface of table or something like that. We just have that interaction between two objects at this point. Now, in one direction and in x direction, but we need to find the components. We have this in negative x direction. We have this with angle. We need just to find the component of the tension force. So this is on the x component to this direction. Tension force multiplied by cosine or sine, like the previous lecture. What? Sine or cosine? The cosine is in the direction of the angle. So the angle is from the x-axis. The x-axis will have the cosine theta. From this direction, it will be t sine theta. The wind forces to this direction. F applied. Be careful for this one. Now, the force is in y. It will not be zero. This one. I will see. You will see that now. Now, the forces in y direction are. We have the weight downward plus F sine 40 also downward in the negative y direction. It will be equal to 4 newtons plus 50 sine 40, sine 60. It will be sine 60, 50 sine 60, which is this will be equal to 4 plus 43.3, which is equal to 47.3 newtons downward. This is the summation of Fy. So we have, this is the kite. We have total y force to downward, which is 47.3 newtons. So it will fall down, right? Okay. What about the x direction? The x direction forces are zero. We have the tension cosine 60 minus the opposite direction, the applied force due to the wind, which is unknown. Now, this is equal to zero. Tension is 50. Cosine 60 is 1/2 minus F applied. Then 25 minus F applied is equal to 0. Then we can move F applied to the opposite direction, which is equal to 25 newtons. Now, the applied force due to the wind force is 25 newtons. Who can tell me now, do we have a balance? Do we have a stationary state for the kite, or it will fall down? The forces in x direction are zero, but the forces in downward are not zero. So the kite will fall down, right? What is the case to make it not falling down? Who can tell me? If you can see that kite in the sky, it is not in this direction. It's direction with an angle, right? This is the right angle, and because of that, the thread is attached at this side, and we have some weight, which is the tail at the end, to keep this angle suitable to make Fy equal to 0. We can find it, this angle. We will not find it now, just another example to solve Fy and Fx with sine and cosine. Any questions so far? So now we have the homework, and at the end of this day, the quiz will be ready. Okay, now another important thing with the red font. We are here. The next week, I think it is even week. Anybody need to come, you see it is empty in general. You can come if you need to have face to face. We have 2 lectures. We have application on Newton's law. Okay, we will take the same material. We will solve different applications. Today we solve one application, which is the gravitational law and the way the moon and the sun and something like that. We will solve using during these 2 lectures more examples, I think. Then in Monday we have the first exam. It will be online. You will have to use look-down browser. For example, Ronaldo cannot use look-down browser. He needs to send me an email and I will prepare something different than that. So this is the second quiz. You need to be sure you can use or cannot use the look-down browser to be ready for the first midterm exam. I think the midterm exam will be 17 questions, 2 of them with extra credits. Your score will be from 15, I think. Okay, in general, I will do this. And you will, I think it will be half-half. It is not full open book exam. I will give you a piece of a sheet formula, or just you can prepare one of it. For example, if you have the book and you need to open that book in that exam, you will not have enough time to look at different resources to solve that exam, that problem. So you will lose the time and you will lose the grades. So you need to understand the concepts for the material to solve that exam. Okay? That's all today. Thank you.
Is the quiz on chapter 3 and 4?
The quiz is mainly on Newton's law, and I think I will put a simple part on projectile motion. Simple. Will not be difficult. Also, it is an open book quiz.
And you're opening it up today, or it's due by the end of today?
No, I will open it today. But you will have less time to do it. I have an idea. What if I need your opinion about that? General, also the person who are online. In general, I put the homework with 10 days. It is a long period. But I think if I put it with open time, do you think that's better? For another semester?
Like, are you saying till the end of
To the end of the semester, yes. To the first period of December, for example. So it is open for you, but if you are late to finish that homework, you will lose some percentage. You need to do that. I will make it up. Also, I'm talking to you who are online. That's it. Good luck. Thank you.
Excuse me. Okay, can you hear me?
I'm trying to online. I'm trying to upload the recorded lecture, but sometimes there is a lot happen when I'm trying to activate my account or something like that. But in general, you can see this lecture on campus, the YouTube video.
Did you say the exam was open book?
The chapter just in Newton's law and a bit of projectile motion. B cap is okay.
You have a. We're not using 192.
Where?
Where the wider.
Yes, we decompose the force. We have this direction, this direction. You mean both of them in the y direction? Sorry. Yes.
The quadrant
Is it 40? Sine of 40? No, sine of 60.
Yeah, that's where I got.
60. Sorry. I look 40 to the force. Where's the force? Where's something? I see 40 on some page. It's not 40. Sine 60. Which is this.
Okay, yeah, that makes more sense. Yeah, I was just.
It is just type.